So in this video we're going to go over what a homogeneous differential equation is. So a differential equation is going to be said to be homogeneous, a homogeneous differential equation, if we can write it in this form. So this is the form where we have the coefficient on the dx term is a function of two variables. So they don't have to be x and y, they could be t and r, any two variables. And if the coefficient on the dy term is a function of the same two variables and the function m and n are both homogeneous functions of the same degree, then we say that the differential equation is a homogeneous differential equation. And we showed in the previous video how to demonstrate whether a function is homogeneous of degree n or not. So to verify that a function differential equation is a homogeneous differential equation, we just need to identify that it can be written in this form and that m and n are both functions of the same degree. So in this case we have dx and dy, and we have a function of x and y being multiplied by dx and a function of x and y being multiplied by dy. So what we see is that m of xy, the function of two variables being multiplied by the dx term, is just the function x squared minus y squared, and n of xy, the function of the same two variables that's being multiplied by the dy term, is just xy. So our function is in the correct form. It's in the form m of xy dx plus n of xy dy. So to verify that it's a homogeneous differential equation, we just need to demonstrate that these two functions are homogeneous of the same degree. And we could do that by inspection. I see that I have a second degree term. So this is going to wind up being homogeneous of degree 2. And x to the first times y to the first is a second degree term because the sum of those exponents is a 2. This is going to be homogeneous of degree 2. We could work it out as well. We could take, like we did in the previous video, replace x with xt. We could replace y with yt, and then do our substitutions, x squared minus y squared, but replace the x with xt, and replace the y with the yt, and then simplify, so we get x squared, t squared minus y squared, t squared, and then factoring off the t squared that's common to both terms, I see I get t squared times x squared minus y squared, which is just t squared times the m of xy that we started with, which means m of xy is homogeneous of degree 2. And then we could do the same thing with this. We could say, hey, let's replace the x with xt, replace the y with yt. So we're going to have x times y, but we're replacing x with xt and y with yt. And this is going to simplify to t times t is t squared times x times y, but x times y is just the original function n of xy, which verifies that n is homogeneous of degree 2. So because m and n are homogeneous of degree 2 and our differential equation is in this form, we have a differential equation that is a homogeneous differential equation. So here's another example where we initially don't start with something that is in this form. So step 1 is to verify that the differential equation we have can be written in this form. So to do that, I'm going to take my differential equation dy dx equals x plus y over x minus y. I'll multiply both sides times xy dx. So if we multiply both sides by x minus y dx, x minus y dx, we wind up getting x minus y dy equaling x plus y dx, and then we can subtract this from both sides, which is going to give us minus x plus y dx plus x minus y dy, which is in the form mxy dx plus n of xy dy equal to 0. So it has the appropriate form. Now we just need to make sure that the functions m and n are both homogeneous of the same degree. So we see that our function m of xy is just the opposite of x plus y. So if we make the replacement xt comma yt, we're going to get the opposite of xt plus yt. But that t can factor out. We'll have t times the opposite of x plus y, which is just t times the original function m of xy. So m is homogeneous of degree 1 because we have a t to the first power. And then we can play the same game one more time with the n of xy. So we see n of xy is just equal to x minus y. It's the coefficient on the dy. And then we can make the replacement. X gets replaced with xt, y gets replaced with yt. So we wind up with xt minus yt. Clearly the t factors out front, and we get t times x minus y, which is just t times the original function. And this is t to the first, so the function n of xy is homogeneous of degree 1. So because this differential equation can be written in this form, with m and n being homogeneous of the same degree, this differential equation, is a homogeneous differential equation.